Good morning, everyone. I'm Dr. S.K. Singh, and I'm excited to welcome you to today's presentation. Today, we'll be exploring the topic of contamination sources, specifically focusing on material outgassing and surface chemistry. Over the next few slides, we'll uncover how these factors impact our work and what we can do about them. So, let's dive in and get started. Now, let's take a closer look at the mechanisms of outgassing. First, we have desorption, which is when molecules leave the surface of a material. Think of it as molecules detaching and escaping into the surrounding environment. Next is diffusion, where gas molecules migrate from the bulk material toward the surface, moving through the material itself. This process is crucial because it determines how quickly gases can reach the surface and outgas. Then there's decomposition, which occurs when the material itself breaks down, releasing gases as a result of chemical or thermal breakdown. This can be a significant source of contamination, especially in sensitive environments. Lastly, permeation involves gases passing through a material entirely, from one side to the other, which can be a challenge in creating effective barriers. Understanding these mechanisms is vital because contamination control is critical in industries like semiconductor manufacturing, aerospace, and pharmaceuticals. Two major hidden sources of contamination are material outgassing and surface chemical interactions, which can significantly impact product quality and system performance. So, by grasping these processes, we can better develop strategies to mitigate their effects and maintain the integrity of our environments. Let's take a closer look at the factors that influence outgassing. First, temperature plays a significant role here. When the temperature increases, outgassing tends to increase as well. This happens because higher temperatures give trapped gases more energy to escape from the material. Next, the material composition itself matters a lot. For example, polymers generally outgas more than metals do, mainly because of their complex molecular structures and higher absorption of gases. Surface area and porosity are also crucial factors. The larger the surface area or the more porous a material is, the more gases can be trapped and subsequently released. Exposure to humidity or solvents can further enhance outgassing, because these elements can either cause the materials to absorb more gases or loosen trapped gases, making it easier for them to escape. Now you might be wondering, what exactly is material outgassing? It's basically the release of gases that are either trapped or absorbed within a material. This process is particularly important in specific environments, such as vacuum conditions or when materials are exposed to elevated temperatures. The common gases involved include water vapor, which is H2O, hydrocarbons, and also carbon monoxide and carbon dioxide. CO and CO2, these gases can impact the environment, especially in sensitive applications like space or high vacuum systems, so understanding and controlling outgassing is essential. Let's take a closer look at some examples of outgassing in different environments. When it comes to spacecraft contamination, one common issue is optical lenses fogging up. This happens because polymers inside the spacecraft release gases that settle on the lenses, reducing their clarity and potentially impacting mission performance. Moving on to semiconductor fabs, a significant concern is the release of organics from photoresist materials. These materials are essential for chip manufacturing, but they can emit volatile compounds that contaminate the cleanroom environment and affect the quality of the chips. Lastly, in vacuum systems, rubber seals are a typical source of outgassing. They release water vapor and other gases into the system, which can interfere with sensitive processes or measurements. Overall, these examples highlight how outgassing can be a critical challenge across various fields, emphasizing the importance of controlling and mitigating these gases to maintain system integrity and performance. Now, let's take a closer look at surface contamination mechanisms. One key process is adsorption, which is when molecules from the environment stick to a surface. This can happen naturally and is often the first step in contamination. Next, we have chemical reactions like oxidation and hydrolysis that can occur at the surface, leading to changes in material properties. These reactions can sometimes cause corrosion or weaken the surface over time. Another important aspect is residue formation, which involves the creation of thin films from airborne contaminants settling on surfaces. These films can be quite persistent and may influence subsequent reactions or processes. So, what exactly is surface chemistry? It refers to the chemical reactions taking place right at the material's surface, and these reactions can significantly impact how materials behave. For example, adsorption affects how surfaces interact with their environment. Corrosion can degrade materials, and catalytic reactions are essential in many industrial processes. Understanding these mechanisms helps us better control contamination and improve material performance in various applications. Let's explore some examples of surface chemistry contamination. First, oxidation of metals is a common issue, where rust forms on iron surfaces, leading to deterioration. Moving on, in the context of silicon wafers, contamination often involves native oxide layer growth, which can impact their performance in electronic devices. In the pharmaceutical world, surfaces can cause drug degradation because of reactive surface interactions, which is a significant concern for product stability. Now, regarding the types of surface interactions, we have physisorption and chemisorption. Physisorption involves weak van der Waals forces, which are relatively easy to break apart. Chemisorption, on the other hand, involves strong chemical bonds, making the interaction much more robust. For example, oxygen binding to metal surfaces results in oxidation, a classic case of chemisorption. Understanding these interactions helps us better control contamination and surface reactions across various fields. Let's take a closer look at some of the key measurement techniques used in surface analysis. First, we have TGA, or thermogravimetric analysis, which helps us understand how materials lose weight as they are heated, giving insights into outgassing behavior. Then, there's mass spectrometry, a powerful method to identify and quantify gases released during heating or other processes. Next is the quartz crystal microbalance, or QCM, which detects tiny mass changes on a surface by measuring frequency shifts, very useful for monitoring film deposition or cleaning processes. Moving on to surface analysis tools, XPS, or X-ray photoelectron spectroscopy, allows us to examine the surface chemistry by identifying elemental composition and chemical states. All these techniques together give us a comprehensive picture of the surface phenomena. When we consider the combined effect of outgassing and surface chemistry, it becomes clear that molecules released during outgassing can deposit onto nearby surfaces. This process can lead to problems like thin film contamination, which can alter surface properties, and optical degradation, which affects the performance of optical components. For example, in satellite systems, mirrors can lose their reflectivity over time due to these contamination layers, reducing the effectiveness of the optical system. Understanding and monitoring these processes with the right measurement techniques is crucial for maintaining the performance and longevity of sensitive surfaces in various applications. Now, let's talk about mitigation strategies to minimize outgassing and contamination. First, material selection is crucial. We want to choose low outgassing materials, such as certain metals and ceramics, because these materials inherently produce fewer volatile compounds. This helps maintain the integrity of our environment and prevents contamination. Next, pretreatment processes play a significant role. Bakeout procedures, for example, involve heating components to drive off any trapped gases before installation. Additionally, working within cleanroom environments ensures that we control airborne particles and contaminants, creating a much cleaner setting for sensitive equipment. Finally, surface coatings can be very effective. Passivation layers, for instance, form protective coatings on metal surfaces, reducing their tendency to outgas or react with other substances. These strategies, when combined, form a comprehensive approach to reducing contamination risks and improving the overall reliability of our systems. Let's wrap up with some key takeaways. Outgassing and surface chemistry are really critical sources of contamination that we need to pay close attention to. These factors can strongly influence the reliability of our products as well as their overall performance. It's not just about avoiding immediate issues, but also about ensuring long-term functionality. That's why proper material selection and implementing effective control methods are absolutely essential. By choosing the right materials and carefully managing surface interactions, we can significantly reduce contamination risks. Remember, understanding these sources helps us design better, more reliable systems and maintain high-performance standards throughout the product lifecycle. For further support, please feel free to reach out to us. We're here to help with any questions or additional information you might need. Don't hesitate to contact us through the provided channels. And with that, I want to sincerely thank you all for your attention and engagement throughout this presentation. Your interest is truly appreciated, and I look forward to staying connected.